Okay, Franklin, we are now live, so whenever you are ready, you can introduce the
Ah,
speaker.
Okay, so let's get started. Welcome, everyone. It's my pleasure to introduce today Benjamin Bichsel, who will be talking about Silq, high-level quantum programming. I have to say that I started playing with Silq a little bit, and it seems really good, so I'm very excited about this talk. Benjamin Bichsel is a PhD student at ETH Zürich, supervised by Professor Martin Vechev. He has led the development of Silq, which is part of a broader effort to bridge the conceptual gap between classical and quantum languages, thus lowering the entrance barrier for non-expert quantum programmers. Beyond quantum programming, his research interests include differential privacy, probabilistic programming, and data privacy for smart contracts. Benjamin received the Willy Studer Prize in 2018 for the best master's degree in computer science, and also an award from Schweizer Jugendforst. And now, without further ado, I will hand over to our guest speaker. Thank you, Benjamin. It's your turn.
Hi, and thanks for the great and thorough introduction. Welcome to this talk on Silq, a high-level quantum programming language. As you kindly said, my name is Benjamin, but I developed Silq together with Maximilian, Timon, and Martin Vechev, and we are all from ETH Zürich. So to give you a bit of context for this talk, the list of quantum languages is growing constantly. So down here, I'm showing a few examples. I'm assuming you can see my pointer and my screen, otherwise feel free to complain. So we have a few examples down here. For example, you may have heard of Q# or Qiskit, and I know that Silq was introduced here 2 weeks ago. So a valid question is, of course, what makes Silq so different? And the answer I would give is that in contrast to other quantum languages, Silq supports a high-level descriptive view on quantum algorithms that expresses the high-level intent of the programmer. So as a consequence, Silq programs are shorter and simpler, they prevent more errors, and they modify the program's quantum state according to an intuitive semantics that follows the laws of quantum physics. So this is a high-level overview of what I hope I can convince you of in the remainder of this talk. So let me give you a quick outline of what this talk will consist of. So first, we will discuss the standard parts of Silq, which exist analogously also in other languages, but I think it's instructive to first describe Silq in a way that you might have seen the description in other languages as well. And then we will move on to the more advanced features of Silq that are novel and unique to Silq. And finally, to wrap up, I would like to quickly broaden the view and discuss more generally how programming language techniques can help with quantum computing. So to showcase Silq, we will use this running example. So here, the task is that you're given a function that takes booleans to booleans, and you're trying to determine if f of 0 equals f of 1. So if f is constant, if f of 0 equals f of 1, then f is constant, and otherwise it's balanced. So in 50% of the cases it's 0, and in 50% of the cases it's 1. Now there is a really simple classical solution to this task, which I wrote here in Silq already. Silq can also handle classical programs. So that's already a great way to start interacting with Silq by viewing like the simplest possible program that we could write to solve this problem classically. So here what we're doing is we're evaluating f on false or 0. We're getting some output. We're evaluating f on true or 1. We're getting some output, and we're just checking if the two outputs are the same. So there's nothing really special going on here, but let me use this opportunity to discuss a bit about the syntax of Silq. So what you can see here is that the input to this trivial solution is a function which itself takes as input a Boolean. So this symbol here indicates Booleans in Silq. And if you're typing Silq programs yourself, you can also use just a standard capital B instead if you're not comfortable with finding this Unicode character on your keyboard. So this is the Boolean. Now the output of f is annotated with this exclamation mark, which indicates that the output of f is a classical Boolean. So this is classical data, nothing quantum is happening here. And the fact that it's classical is marked by this exclamation mark. And finally, this arrow here indicates that f is a function from classical Booleans to classical Booleans. And the exclamation mark indicates that the function is classically known. For the purpose of this talk, you can ignore this exclamation mark, or rather assume that the exclamation mark is always there whenever you see a function. Okay, so this was a really, one thing I wanted to mention exactly is this colon equal, which is also a bit of a peculiarity in Silq. What this indicates is that we are assigning the output of f on false into a fresh variable output 0. If we were to overwrite this variable, then we would just use the standard equals here. But the colon equals indicates that we are allocating a fresh variable for this. So this was a very simple classical solution to this problem here. So I would like to introduce the quantum solution, which many of you may know already. But before that, let me give you a very quick background in quantum computation, which is hopefully not really needed, but it's always good to get everyone on the same page. So as you hopefully all know, in contrast to classical states, which are shown here on the left, so you would have a single bit would have state 0 or 1, quantum states on the right also enable superposition. So you don't only have the state cat0, which corresponds to state classical state 0, and cat1, which corresponds to classical state 1, but also superpositions or linear combinations. And the same thing happens if we look at multi-qubit states or multi-bit states. So here we have 2 bits. And these 2 bits, for example, here the first bit is in state 0 and the second bit is in state 0. And here the first bit is in state 1. And again, we get the analogous thing for quantum states, where this state here, 0 tensor 0 corresponds to the 0, 0 state, and 1 tensor 0 corresponds to the 1, 0 state. And again, we get superpositions. So hopefully completely boring for most of the attendees here. And the second concept we need is that of a quantum oracle, which allows to run a classical function such as the function f we have seen before from Booleans to Booleans on a quantum computer. So ideally, we would like to just have a quantum oracle or a quantum circuit that takes the state holding x and puts it to f of x. Unfortunately, this is not possible in general. The main reason is that f may not be reversible. And quantum computation can only support reversible computations. So from the output, you should always be able to infer the input, which is not possible in this scenario, for example, if f is constant. So the general purpose construction that people usually use in this case is that of a quantum oracle, which doesn't just put x into the oracle, but also y. And the idea is that x is the input and it's preserved. And y is used to store the output by computing y XOR f of x. So hopefully, whenever we use this oracle, y will be 0, in which case we actually get f of x here. So let me illustrate this concretely here. So if we put 0 as x and 0 as y, then we will get, still we will get x, but we will get f of 0, so f of x in the second qubit. And if we put x as 1 and y still as 0, then we still preserve the input x, but we get f of 1 now in the second qubit. And of course, this function is also defined when we put y as 1, but actually we don't care because we never intend to set y equals to 1. And as you hopefully know, quantum computation is always linear. So this operation extends naturally to superpositions. So here we have a superposition over possible values of x and y. And what we would do is we would component-wise apply this function to every aspect, to every summand here. So we preserve x and we XOR y with f of x. So this is hopefully all pretty straightforward for people who have some background in quantum computation. So let's get back now to our running example. Namely, we are now using the quantum oracle for f. And using the Deutsche Choser algorithm, which is the quantum algorithm that can solve this task more efficiently even than the classical algorithm of determining if f of 0 equals f of 1. And the nice thing about the Deutsche Choser algorithm is that it only requires a single query to the quantum oracle, in contrast to the classical query or the classical function, which required 2 queries. So let me step through the Deutsche Choser algorithm. Again, there's still no Silq happening here. This is just introducing Deutsche Choser as you would normally see it in a standard course on quantum computation. So what we're seeing here is that we have 2 qubits, which are indicated as lines here. We initialize the first qubit as 0 and the second qubit as 1, which gives us a state of 0 tensor 1. Then we apply Hadamard to the first qubit. And because Hadamard moves 0 to the plus state, which is essentially 0 plus 1 if we ignore the normalization of 1 over square root of 2 here, we move the first qubit of 0 to the plus state. So now we get the state plus tensor 1. Now we apply Hadamard to the second qubit, and Hadamard moves the state 1 to the minus state, which is essentially 0 minus 1, again if we ignore the normalization here. So we now get the state plus tensor minus. We can now apply the quantum oracle, which leaves us with this nasty state. I will not really discuss how we get from here to here, but this is a, let's say, medium hard challenge to compute this in a back of the envelope calculation. But the interesting thing that we're observing here is that after we apply the quantum oracle, the second qubit is in the minus state and it's unentangled with the rest, so its state can be described independently of the first qubit. And the first qubit is, again, if we ignore normalization, is a linear combination of ket 0 and ket 1, where sometimes you have a prefactor of -1, which depends on f of x. We will see this later on in a bit more detail, but the idea is that depending on f of x, this state could be ket 0 plus ket 1 or ket 0 minus ket 1, or minus ket 0 plus ket 1, and so on. So now the Deutsche Choser algorithm figures out, or we figure out as the people analyzing Deutsche Choser, that because the second qubit is unentangled with the first qubit, it can be safely ignored from the state. So what we can do is just forget about this second qubit, and just keep the first part, which is again this linear or a superposition of ket 0 and ket 1. And applying the Hadamard to this will give us exactly the right state. I will discuss in a second why, which is ket 0 if f of 0 equals f of 1 and ket 1 otherwise. And so if we measure this, after the measurement, we get a classical representation of 0 or 1, depending on whether f is constant or balanced here. So let me investigate this in slightly more detail in a separate slide. So the question is, well, why do we get from here using Hadamard to this state here? And we can easily figure this out by a case distinction. So we can just check, well, what happens for possible instantiations of f. So for example, if f of 0 equals 0 and f of 1 equals 0, then what will happen is that this one is always 0. So the -1 is actually a factor of 1, so it goes away, which means that we're actually mapping the 0 plus 1, which is the plus state, through Hadamard, which yields 0. And this is exactly what we want, because f of 0 equals f of 1, so we should expect a 0 state here. And through a similar case distinction, we can fill out the rest of the table. The details are not so relevant, but the key idea is that the prefactor of this ket 0 and ket 1 is always chosen exactly in the right way to ensure that we get to the right state in the end. Okay, so as a minor side note, we're also ignoring a global phase here, but again, this is more of an advanced thing that is not so relevant to follow the key outlines of this talk. Okay, so now we have seen Deutsche Choser as it would be presented in a standard quantum computation course. So let's see how we can straightforwardly translate this circuit that we saw before into Silq. So the idea is that we are given the Silq code, and this Silq code essentially stands for the circuit that we have looked at before. So let's investigate this code line by line. So first of all, this code as input expects the quantum oracle, which takes 2 quantum booleans and returns 2 quantum booleans. So it modifies the 2 quantum booleans. Now contrast this to the function f, which we have seen before, which took a classical boolean to a classical boolean, and the exclamation mark marked that this boolean was classical. Now there's no exclamation mark here anymore, which indicates that now we're actually working in the quantum world on quantum booleans. So at first, we should initialize 2 qubits, which we call x and y, by 0 and 1 respectively. And this column B here indicates that we interpret 0 as a quantum bit cat 0. Now, as the next step, we want to apply the Hadamard operation to both x and y. And the notation here, again, is specific to Silq. So let me introduce this a bit more generally over here. So what's happening if we apply Hadamard to x is we feed the wire called x into the Hadamard operation, and this wire is gone now. So if we want to name the output wire or the outcoming wire, we need to do so explicitly. So what we would write here is we would explicitly assign a name for the outcoming wire y here. But what we're doing over here is actually want to preserve the wire. So the reasonable thing to do is to just preserve the name also. So if we use this common idiom that is widespread in Silq code of x colon equals h of x, then what will happen is that x goes into the Hadamard operation, and we will name the outcoming wire x again. So this is what we do here. So these 2 lines just apply Hadamard to the 2 respective bits here. So sometimes this consumption of the incoming wire is a source of confusion in Silq. So let me illustrate this in a bit more detail, how h consumes its argument. And let me do this by demonstrating an incorrect program that Silq would complain about, and rightfully so. So what we're writing here is we apply Hadamard to the x wire. We're naming the output y, and then we try to apply Hadamard again to the x wire, naming the output z. Now, I would argue that the natural way to translate this into a quantum circuit is what we're seeing here. So we're using the x wire twice, once as input to the Hadamard, which produces the y wire, and once as input to the Hadamard, which produces the z wire. And this is, of course, not possible because this operation here would require cloning, and this is just not physically realizable. So Silq disallows this type of code, but what it does allow is just naming the output wire the same again, right? So here, this code would apply Hadamard to x, name the output x, and then apply Hadamard again to x and name the output x. And what this gives us is just applying Hadamard twice. So this is just to avoid as much confusion as possible about this consumption of Hadamard of its argument. But let's get back to our Deutsche Choser algorithm. So remember, we initialized x and y to 0 and 1, applied Hadamard to both x and y. So the next step now is applying the quantum oracle to both x and y. And this works exactly as before, except that now we have 2 arguments and we also have 2 outputs, but nothing surprising is happening here. Then as a next step, we observed before that this value is unentangled with the rest, or this quantum bit is unentangled with the rest, and we just claimed, oh, okay, then we can just ignore it. Now, this is a bit subtle here, because just ignoring a qubit in a state is physically equivalent to measuring it, just for weird reasons of quantum computation. So in Silq, we actually make this explicit, and we specifically point out that actually ignoring the second qubit here is equivalent to measuring it. So we indicate that we measure qubit y, but we know that this has no effect because y is unentangled with the rest of the system. Now to conclude, we apply the Hadamard operation to the x wire here, and we measure the output and we return it. And again, we will get the correct result. So this was a rather straightforward translation of the quantum circuit, as you would see it in a standard course. So now let's move on to the more advanced features of Silq and ask, what is an idiomatic implementation of Deutsche Choser in Silq? So what is the most intuitive way to prepare this key state which is essentially cat0 plus cat1, but has factors of -1 in all the right places, such that when we apply Hadamard to this state, we get exactly the right solution back. So to this end, let me introduce two more advanced features of Silq. The first feature is that of a quantum conditional. So what we're having here is we're saying if X, then apply the Hadamard operation to qubit Y. And the intended semantics of this is if we have this state where the first qubit is qubit X and the second qubit is qubit Y, then only to those parts of the superposition where X is 1 should we apply the Hadamard operation to Y. So what will happen is in the first part of the superposition, nothing happens because X is 0 here. But in the second part where X is 1, we apply the Hadamard operation, so which maps 1 to minus. So this, I would say, is quite close to what you can do in existing languages and also what you can do in circuits. It's just a controlled application of the Hadamard gate controlled by X. Now, things get a little more tricky if we apply more interesting language features in Silq. So what we're doing here is we're saying if X, then change the phase of X, and this phase of pi has the effect of changing the sign from, flipping the sign from +1 to -1 and vice versa. So what's happening here in terms of intended semantics is that if we have the state of 0 plus 1, then again, same story. For 0, nothing happens, but for 1, we apply this phase operation, which switches the sign from a plus to a minus. Now, I would argue in Silq, this is rather straightforward, but already if you're trying to compile this now or express it in existing languages, you have to think a bit. Because the problem is this phase of pi, this is pi itself, just a global phase shift, which has no effect in quantum computation. The only reason why it has an effect is because it's in a quantum conditional here. So we can actually not come up with a gate for this phase pi and then do a controlled application trick as before, because this gate would be the identity operation and we would get the wrong result. So what we can do instead to compile this specific thing is just compile it atomically to a set gate, which will work, but as I said, requires a bit more thinking. So already you can see that the gap between Silq and quantum circuits is increasing. And this is an overarching theme in Silq in that it describes the effect on the quantum state over here quite straightforwardly, but it doesn't have the expectation of being trivial to translate to circuits. Now, there's always a translation and the compiler can figure it out, but the mental model is over here in terms of Silq programs and operations on quantum states. So this was the first primitive. Now let's move on to the more advanced primitive, which is much more unique to Silq than this quantum conditional. And let's in particular look at how Silq deals with temporary values. So what you can see here is a small code snippet which computes the OR of A, B, and C and stores the result into D. So I think the intended semantics of this is again quite clear. If we have a state where A is 0, B is 1, and C is 0, then the OR of this should be 1, right? OR of 0, 1, 0 is 1. So we should expect to get this state here, where we preserve the inputs A, B, and C, and store the output, the OR of A, B, C into an additional qubit. But how can we translate this into a quantum circuit? That's actually quite challenging. So let me discuss how this can be done. To this end, we are constructing a quantum circuit with 3 inputs, A, B, and C, and an additional output which stores the OR of A, B, C, which we initialize to 0, and then we modify this 0 to make sure we get the right result over here. So what we will do in order to compute the OR of ABC is first compute the OR of AB. So again, we initialize a temporary value to 0, compute the OR of AB, and then use this result to compute the OR of this with C, and we will get the OR of ABC. So I can demonstrate this in terms of quantum state. So again, if we are here and we have the OR of, we have values for A, B, C, then we compute the OR of AB, store this into an additional qubit, And then we can store compute the OR of ABC, store it again into an additional qubit. And now we would like to be done, and classically we would be done. We would just forget about this temporary value over here. But in quantum computation, this is not so easy, because if we just drop this value here, as I discussed before, this will be implicitly measured, which would lead to a collapse of this state here, which in this example is not an issue, but if we would have a superposition, this would completely screw up our computation. So we actually need to safely discard this temporary value over here. And the way this is usually done in quantum computation is through uncomputation. So what we can do is we can insert the inverse operation of the OR that computed the OR of AB back here, which resets the temporary value back to 0. And because 0 is unentangled with the rest of the state, now we can actually safely discard it. And what we will get is exactly the expected result up here. But as you can see, in Silq, this is quite easy to do, whereas if you have to construct this in terms of a quantum circuit, you have to remember, first of all, to place this uncomputation. You have to apply to the right operations over here, and you have to make sure that you're actually applying the right operation. So actually the inverse of the OR which you computed over here. So to give you a slightly different perspective of what is happening in Silq behind the scenes, let me expand this line here a bit and explain line by line what is happening. So what Silq would do is it would first get inputs A, B, C. It would store the OR of AB into a temporary value. It would use this temporary value to compute the OR of ABC. But again, as before, we still have this nasty temporary value, the OR of AB, which we need to get rid of. So Silq would implicitly forget this temporary value by inserting the appropriate uncomputation gate, and it would just get rid of it exactly as we would expect. So both of these statements are valid Silq codes, or both of these snippets. But of course, you would prefer this because here everything is explicit and this is much simpler. Right. So of course, this does not necessarily always work. So it's actually important that Silq is concerned with safety. So in particular, this uncomputation that we're seeing here only works, as in only correctly drops this value in stepping from here to here, if the following two conditions are met. So first of all, the temporary value that we want to uncompute should be computed by a Q-free function, which means that the function is essentially classical. So for example, the OR function is classical. It can be applied to quantum inputs, but it's classical at core. But for example, the Hadamard operation is not Q-free because it's a completely quantum function. And so this is the first condition. And the second condition is that the temporary value depended on values which were preserved. So here we can see that this temporary value, the OR of AB, depends on AB, and AB are still around. So we can actually leverage them for uncomputation, which is the second critical property that Silq is checking. So Silq checks these two properties automatically and only supports automatic uncomputation when they are met. When they are not met, Silq would complain and leave the programmer to figure out if maybe the programmer made a mistake or if things are actually fine and manual uncomputation is an option in this case. So to look at this from a slightly different perspective, let me see how we can actually define a Q-free function like this OR that we used before to be used in the slide before. So here I use this OR operation, which is a native primitive in Silq, but of course some languages don't even support this. So you might be wondering, how can you even implement the OR in Silq? So, and in Silq, this is really easy. I just implemented this here using, again, a lot of automatic uncomputation. But this is just a side note. What I want to focus on is the signature of this function here, of this OR function, because what we are writing here is we're indicating that the argument A is const, meaning that this my OR function preserves A. A is not consumed. So after calling my OR, A will still be around. And we're annotating the function as Q-free, which again means that the function can be described classically. It's essentially classical, but it can be applied to quantum inputs. And because this pattern of preserving the inputs and being classical is so common, we also offer syntactic sugar for this occurrence. By writing lifted, you can indicate that the arguments are left constant and the function itself is Q-free. And no matter which definition you use, this is just syntactic sugar for this one. If you now use the function and you apply my OR of A, B and store the result into C, you will preserve A and B as indicated up here by the signature of the function. You will compute a new temporary value or a new value that holds the OR of AB. And if you want, you can leverage automatic uncomputation later on for this, because we know that this function is lifted. We know that automatically uncomputing this temporary value, if it turns out to be a temporary value, is actually possible. So let me quickly investigate how automatic uncomputation, or rather manual uncomputation, is handled in other quantum languages. So here, as a quick recap, we have A or B or C in Silq. In Q#, for example, what you would do is you would pretty closely follow the circuit description view I had before. So you would allocate the temporary qubit, which is implicitly initialized to 0. You would store the OR of AB into the temporary qubit. You would use the temporary qubit to store the OR of TC into D. And then you shouldn't forget the uncomputation, which now uncomputes T by undoing the operation OR from before. And if you would forget this line or misspell it somehow, you would get a mistake here. And there's also an alternative approach which semi-automatically handles this. For example, you can see this approach in Quipper, which has this specific language feature with computed, which first computes the OR of AB, stores the result into T, and then uses this T to compute the OR of TC. But again, you have to explicitly remember that you need to type with computed and thus handle or mark this temporary value as temporary. And this is not safe, or not as safe as in Silq, because it doesn't check the same safety conditions that I discussed before. So uncomputation may actually lead to unexpected results in these languages, whereas in Silq, it's easier to write, even compared to this simplified version over here, and it's also completely safe. So using these two new language features, let's write or investigate an idiomatic implementation of the Deutsche Choser algorithm, which now is much simpler. So what we can do is we have a single qubit X, which we initialize to 0. We apply the Hadamard operation. So we get this superposition of, we get the plus state, which is a superposition of 0 and 1. Now, if f of x, we apply the phase shift here, which switches the sign. So what will happen here is we first evaluate f of x. So what will happen is that in every summand here, we get f of x as stored in a new qubit. We apply the phase change if f of x is true, which gives us the -1 to the f of x, because if f of x is 0, then we don't do anything, and this is 1 as expected. And if f of x is 1, then this gives us a factor of -1, which exactly corresponds to this phase shift here. And then when stepping out of the conditional, we leverage automatic uncomputation to get rid of this f of x here. So here we already have the key state that I discussed before. So if I apply Hadamard to this, we get exactly the right thing. We get 0 if f is constant and 1 if f is balanced. So measuring this will give us the right result. Okay, so this was a brief introduction into Silq. So let me now move on to a live demo, which I hope will work. So I have prepared, I'm hoping you now see my demo file, which consists of Silq examples that are partially wrong. And the plan is that we go through these examples line by line. I explain why Silq flags this as wrong. why they are actually unsafe, why they should be flagged as wrong, and in some cases, how to fix them if that is even possible. So the overarching theme here is that Silq is very safe in that it always already statically, before you even run the code, tells you if something is wrong and will not lead to a valid quantum program. So in this first example here, we're trying to apply a conditional measurement. So we have a qubit C and a qubit X. And if C, then we try to measure X and then return the value. Now, this is not possible because C is a quantum bit. So we don't actually know here as the compiler or the simulator of this code, whether or not we should apply the Hadamard. This would require measuring the qubit, which we don't want to do because this would destroy the superposition. So you can't actually run this code as is, but what you could do is you could indicate that this is classical here. And in this case, the type checker of Silq now runs through because conditioning a measurement on classical information is totally possible. Now, this next code snippet here tries to reverse a measurement. And this is just generally not possible. There's no way to fix this. So if we're trying to reverse a measurement, then this operation is unphysical and Silq must complain here. But as a quick side note, not all languages actually figure this out statically. So already this can be seen as an advantage of Silq over other languages. Now we can also try to trick Silq by not giving it a measurement explicitly as a function, but a function from Booleans to Booleans, and maybe this function contains a measurement. So Silq detects this and says, oh, actually, this reverse function must be M3, which indicates that we should promise that the function we are giving here doesn't contain a measurement. And if we do this, Silq doesn't complain anymore because whatever function we have here, as long as it doesn't contain a measurement, we are safe. Now, this next snippet is a bit more evolved or involved as it tries to apply an implicit measurement. So here, we try to compute x modulo 2. So x now consists of multiple qubits, which are interpreted as an unsigned integer. And we are computing x modulo 2 and returning x. But the signature makes it seem as if x is being consumed. So a caller of this function would assume that x is gone after this call. But of course, it's not, as we can see from the function body. So Silq would complain, and it says parameter x is not consumed. And it even suggests that you could return it, but most likely what you want to do is annotate it as const. So if you annotate this as const, now you promise that x will be preserved after calling this function. So Silq no longer complains. Now this next function we already saw before. Here we are trying to use a consumed variable. So we have x is being consumed as it is put into a Hadamard as the argument. And after it is consumed, we are trying to return both x and y. But this is, of course, not possible. There is and Silq complains that this identifier is unidentified because it was consumed here. So it's no longer accessible here. So one thing to here maybe to fix this program is to accept that, well, okay, I guess that's true. X is no longer here, so let me not try to return it anymore. Now, an interesting thing that actually works in Silq but doesn't work in most existing languages is overwriting variables. So what we're having here is we have a function overwrite, which expects two arguments, quantum bit A and a quantum bit B. It stores the OR of A, B into D, and then it overwrites D. Typically, this is a big no-no in existing languages or even in quantum computation in general, because overwriting a value, again, is analogous to measuring it. So this would probably have unintended side effects in other languages. In Silq, this is totally fine because we can implicitly uncompute the old value of D. So overwriting this D by 0 will give exactly the right result. It will first uncompute D and then ensure that D is in the 0 state, which it actually already is after uncomputation. And there will be no implicit measurement happening here. now in this, oh, okay, this is outdated, right? So let me show the error here, actually. So what we are having here is we are trying to uncompute a function or a temporary value, this x of a, which depends on a, but a was consumed. So x of a consumes a and negates it. And if we try to uncompute it here when exiting the function, then we would have to completely get rid of this value. So if we investigate this concretely as a state, if a is in state 0 plus 1, then after applying the x here, we would be in state 1 plus 0 because we switch 0 to 1 and 1 to 0. And after uncomputation, we would need to drop this value because that's what uncomputation means. And we would get the empty state, which is clearly not what was intended here. So one way to fix this is to annotate a as const, which would indicate now that if x tries to consume a is first being duplicated before the consumption. So duplication sounds very dangerous because it sounds a lot like cloning. So let me explain in a bit more detail what is meant here. So duplication, a possible implementation here is that we have the qubit A, we initialize a new qubit B to 0, and if A is true, we flip the qubit B, which means that now we are in state 0, 0, 1, 1. So we cloned the first qubit into the second qubit in some sense, but this is not the unphysical cloning, which would map the 0 plus 1 state, which we had above, so the plus state, to plus plus. So cloning is unphysical, but duplication is not. And if we write const here, then we would get exactly the right behavior here, or most likely the one that was intended. And as the last example here, here we are trying to uncompute a non-Q-free function, this Hadamard operation. And this is really just not possible due to strange mathematical reasons. I can discuss this more, but the bottom line is that you can do a back of the envelope calculation that shows that uncomputation is not possible in this case. So again, Silq would disallow this. So this was a quick demo of the safety features in Silq. So if you're excited about Silq, it is very easy to install. You can just follow our installation instructions on our webpage. And as a starting point, I would recommend that you solve the task that is described in this URL here. This is a good way to get started with Silq, and it asks you to do some to solve a very simple exercise in Silq that is hopefully instructive in getting your first contacts with Silq. Now, to wrap up, as discussed, I would like to quickly broaden the view. So essentially, I see Silq as a connection of language design and quantum languages. Language design is from the domain of programming language research. Quantum languages are from the domain of quantum computing research. But I think programming language research more generally has a lot more to offer. There is a lot of work in compilation, static analysis, verification, synthesis, and much more. And many of these tools that we have available in programming language research should also be a valuable tool to address many of the open challenges that we are facing in quantum computing research, such as circuit generation, circuit optimization, error correction, and much more. So my hope is that in particular, the automatic uncomputation that we have introduced in Silq will allow us to apply many of the tools we see over here more naturally to the open problems we face in quantum computing research. So thanks a lot for your attention. This is it from my side, and I'm happy to take questions.
Thank you very much, Benjamin, for your talk. So does anyone have questions to Benjamin? Let me see on the chat if there is anything. I don't think so. Does anyone want to ask something before I ask my own questions? So
I have a question. Sorry,
okay.
this is Bichsel also from Portugal. I would like to know up to how many qubits can you go actually in superposition or full entanglement, and so how do you actually execute this on a classical machine, or is it always assuming some kind of quantum chip available?
Right. Okay. So let me first answer the second question. I actually have a backup slide for this. So the computational model we are assuming here is that we are operating mostly on a classical computer over here. And in this classical computer, we will also prepare quantum circuits, which are then dispatched and sent to a dedicated quantum computer. And this quantum computer can then apply the gates in this circuit and potentially also apply measurements and return the measurement results. And we're getting a particularly powerful model here if we also allow partial measurement here, in which case then we could then continue the computation based on the measurement results. So this is, I hope this answers your question on the computational model or what the intended plan is. So feel free to interrupt me if this was not the case.
No, that's fine. No, that's clear. Thank you.
Otherwise, for the first question regarding how many qubits you can scale to, so there's two possible interpretations of this question. The first one is how many qubits can anyone scale to in some sense? And this then would be a question about quantum devices, like what is the state of the art in terms of physically building these systems. And I'm no expert there. And this is also, I would say that Silq is not really about that. Silq is just about leveraging, like assuming that existing quantum computers become widely available and are highly reliable and all the good properties you would expect from a reasonable computation infrastructure. Assuming this, we want to give the developer a tool to intuitively, quickly, and safely express the algorithms they want to be then compiled down to a quantum computer. And in this case, I mean, the number of qubits for this really doesn't matter, right? Because we're not actually simulating. Silq does offer a simulator, but long term, of course, the goal is to actually run this on a quantum computer because the simulator necessarily will not scale. And for compilation, the number of qubits is not an issue at all, right? So, I mean, pick whatever number and assuming the compiler will be linear in the program size or the number of qubits, which is a reasonable assumption, we should be able to handle it in Silq. Does this answer your question?
Yeah, sure. I mean, I'm of course more interested in saying that you can go up to 100 qubits, superposition or fully entangled. And if you do that, then you do require a lot of memory from the classical machine to execute your quantum circuit. So it's more along those lines that I'm reasoning.
Right. Okay. So I don't have exact numbers for. I think you're essentially asking about our simulator then. And I think the simulator handles like 30 to 40 qubits, something like this, but I'm not sure. And again, I would stress that this is not really our contribution, right? The goal is not for people to run Silq code, because as you note, this will choke quite quickly. The goal is more long-term, to have a compiler for Silq to a realistic quantum machine. Unfortunately, currently, there is no really good quantum machine out there that could handle the types of tasks that would be interesting to solve. But assuming this exists, then the compilation task really doesn't depend on the number of qubits. So if you run Silq today and you run it simulator, then you will be highly constricted. Long-term, assuming quantum computers will be highly available, this will not be a concern. Our contribution is the language, not the simulation.
Okay, thank you very much. Thank you.
Sure.
Thank you for the question, Professor Bertels. Does anyone want to ask some other question to Benjamin?
I can unmute the folks that have questions in the chat. Just a second.
Yeah.
So I'll go in order. Paolo.
So Benjamin, do you have any plans of extending Silq to other paradigms of quantum computing, such as continuous variable, quantum computation with Q modes instead of qubits, or something like adiabatic quantum computing or some other modules?
I'm not sure if I understand this question. Can you say that the first thing again, the first possible extension? I didn't catch that.
Maybe extending it to deal with continuous variable models such as Xanadu has been using lately to deal with Q modes instead of qubits. I think that's something.
Okay, I don't think I'm familiar with this. Are you saying that you would have a generalization of a qubit that doesn't only store 0 or 1, but superpositions of much more values, even potentially a continuous amount of values? Is this what you're saying?
Yes, that's the math is a bit different from the one that we are that I'm used to applying. But yes, that was my question.
Okay. Yeah, I think, I mean, I wasn't familiar or I wasn't intimately familiar, let's say. I mean, I know that there are generalization to Q-trits and this kind of stuff. And this could be something like, I mean, Q-trits are qubits that essentially store more values, right, than just 0 or 1. So this would be something to investigate during compilation, for example. But like the other directions you mentioned is not something we currently have on our list. I think I would say we are in the somewhat standard computational model here, and the directions that interest us are more like staying in this computational model. How can we solve more open problems such as these ones, right? Like especially the compilation task, I think is very interesting to investigate also in the context of Silq, because we expect that from the high level information we're getting, we should be able to come up with much more efficient circuits than you can get from low level views. So this is more the direction we plan to take Silq into.
Okay, thank you. I see that there is a question in the chat here. There is some comparative between Silq simulator and other concurrents in terms of performance.
Right. Yes. So this is an interesting question. As a general caveat, I would stress that, again, the simulator is not really our contribution. So we haven't, this is just to enable the use of Silq and to run like small programs as the ones that I have shown you here. So we didn't spend a lot of time on first of all, not a lot of time on improving its efficiency, and second of all, also not a lot of time on comparing it to other work. We do know that it can be more efficient, significantly more efficient, even exponentially so, I think, than some other simulators out there. But this is more due to the inefficiencies of these simulators. So if we were to compare to state-of-the-art simulators, then we would definitely lose, because this is not the goal, right? This is just for someone who downloads Silq and wants to see what they are programming. This is a helpful debugging tool, so to speak, but the goal is not to use the simulator now to simulate thousands of qubits, at least not for now.
Okay, thank you. That question came from Gustavo Isidio. Does that answer your question, Gustavo? Okay, great. Does anyone else?
I do have a question.
Okay, yes.
Well, first of all, thanks, Benjamin, for the very interesting talk.
Thanks.
I didn't quite get what consuming a qubit means. Does it mean that a qubit will have to go through a unitary transform?
Yes. So what I mean by consuming a qubit, I think it's shown quite well back here. Well, I mean, really, maybe a more helpful way to phrase it would be consuming the wire, right? Because, I mean, here what you can see is that the input wire X is being consumed by X. So this input wire now is gone, and the output wire is being named Y. So you can say that the qubit is still there somehow. We just apply the unitary to this qubit. But our thinking in terms of the language is that the old qubit vanished and the new qubit appeared. But essentially, I agree with you. Yes, this is applying a unitary. It's just like our mental model is a bit different, but your interpretation is correct, I would say.
Okay. And when you said if you say that the qubit is const, that means that it will not go through a unitary transformation. Is that right? Because in the last examples you showed there was one piece of code in which you duplicated the qubit, or you did something. Yes. Yeah, that one.
Right. So okay. So let me explain this in slightly more detail. So if I annotate this as const, what would happen is before I apply the x to a, I would duplicate the qubit. So what would happen is that I get this here. If I apply the x, I would apply the x to the temporary value here, which would, let's see, which would move this to 0 and this to 1. And so after dropping this second value, I get exactly what I would expect. So I just drop this, which is possible by uncomputation. So I get 0 plus 1 again, which is exactly what I had in the first place, which also makes sense because here I have an if without any body. So you should expect that the input state is the same as the output state. So the duplication I mentioned is this step from here to here. This is automatic duplication. Does this answer your question?
Yeah. So that means that, and that happens every time you define your argument as const.
Exactly right. But sometimes it is easier. So let's see if I think there was an example somewhere. Okay, there's no. Oh, here there's an example. So here we declared a as const. But then we don't actually apply an operation. We use if a, then apply the x to b. And if you're familiar with quantum computation, you would say, well, that's just a C0 gate.
Yeah.
And this is a helpful way to view const. Const indicates that this qubit only acts as a control.
Yeah. Okay.
So you can still, in some sense, apply a unitary to it, but it will act as a control, so it will be preserved. This is why we call it const.
Oh, I see. Okay. All right. Great. Sorry. Last question.
Sure.
Does your compiler output QASM, so that for example, could compile code and then run it on real quantum machines? IBM.
Right. Great question, and I think I wasn't clear enough on this, or not clear at all. We currently don't have a compiler. This is on our list. We know that a compiler exists. So we have investigated this in detail for our publication, like ensuring that compilation is actually possible. But like actually coming up with a compiler also that is as efficient as possible is still a plan of ours. We recently made progress. There's a publication that should appear shortly on just handling uncomputation in the compiler, which I see as the biggest challenge here. So hopefully there will be more progress on compilation soon. But currently there is no compilation. There is only the simulator if you want to use it.
Okay. Okay, great. Thanks.
Sure.
We have another question here on chat. What's the next step for Silq?
Right. So that's actually the perfect follow-up question, right? Because as I just said, one important step is especially also because this is what people talk about most is compilation. So that's definitely an interesting task. But as I discussed, right, there's other interesting tasks. So for example, static analysis is something I think that could be very interesting to do, doing static analysis in Silq, because if you think about it, static analysis in existing languages is quite nasty because these languages always get obfuscated by uncomputation code. And in uncomp, because this happens behind in Silq, because this happens behind the scenes, this is much easier, hopefully, to account for in the static analysis. So that's another example. So these are the main ones. As I said, there's more here, but I should also stress that Silq itself is already an interesting contribution without even having the compiler, because, and this is, by the way, also the reason why we didn't immediately do it, because currently there are no realistic quantum computers anyways. Google made great progress, but like for solving realistic tasks, it's still not really the way to go, quantum computers. So just having the language is actually much more important, because this allows us now to express quantum algorithms efficiently and intuitively, and all the good stuff you would like to have. And compilation to me is a second order concern. This is also why we proceeded this way, by first creating the language and then later on thinking, how can we compile this?
Okay, thank you. One last question. Anyone?
I have a small question.
Hello, Andre.
Am
Go ahead.
Hi.
Hello. Thank you, Benjamin, for your interesting presentation and for everything that Silq has to offer, show us. You mentioned in that slide that one of the areas you want to mingle all the areas, programming language and quantum computation. On the quantum computation side, there's a mention of the error correction. Maybe Silq doesn't do it yet, but about quantum error correction, sometimes it involves more qubits, a lot more qubits generally to perform it. How do you think that Silq will approach that problem, or if it has approached yet?
Right. So currently, like as I said, we don't have a compiler as of now. But if we do, our plan, or my plan would be, first of all, to create a compiler that assumes a perfect quantum computer, which is completely unrealistic, but that's usually the first. Perfect gives you the right result. And then you would have to add error correction as a second order thing. So as you say, error correction is a huge problem in practice. Like once you try to add enough error correction, often your algorithm becomes much less feasible. And I don't have a strong answer today to this, but again, there is some hope that using the high-level insights we're getting from Silq will be useful in improving the error correction as well. But I wouldn't expect that this takes us from non-feasibility to feasibility. So I'm hoping there will also be progress more generally in error correction independent of Silq, and also in devices, right? If you get much better devices, you will also need less error correction, which is an alternative approach. So I see this as largely orthogonal to our research direction, but we may be able to make some contribution at least towards something that works well by high-level insights gained from Silq.
Okay, thank you.
Okay, thank you. So I think you can wrap up now. So thanks a lot for the talk, Benjamin. I learned a lot about Silq today. I'll keep studying it, and I hope I can send you an email when I start having more questions, which I will certainly have.
Sure.
And I would like to thank all the people who attended this talk and participated with a lot of good questions. Thank you all. And last but not least, I have an announcement. The next QC talk will be on March 17, which is next Wednesday, at 5:30 Central European Time, which is 4:30 p.m. in Lisbon, or 1:30 p.m. here in Rio de Janeiro, where I am right now. The speaker next week will be Thomas Gabor from the Institut für Informatik, Ludwig-Maximilians Universität München, Germany. The title of his talk will be Towards Quantum Artificial Intelligence. So we hope to see you here next week. And once again, thank you and goodbye.
Franklin, I'm sorry, the correction is not next week, it's on the 17th.
Oh, no. Oh, 17 years. I'm sorry. Yes, I mean, I'm kind of lost on time.
Okay.
Yeah.
All right. Yeah. Corona.
2
Corona
weeks from
does that.
now. Yes. 2 weeks from now. Yes. 17.
weeks time.
March 17.
Okay. Thank you.
Thank you, Peter.